Hey guys, welcome back to Genius Learning. All right, in the previous video, part 4 of projectile motion, I showed that this arrangement here, the final velocity vector equation, was used to find the time at the max height. We also found the initial velocity, given that we had the initial velocity in the y direction and we had the initial velocity in the x, and we also found theta equals 38.39 degrees. Okay, so we used this velocity vector triangle and we found those things. Now we're going to use the displacement vector to find a couple more things. Okay, so here I have the same setup, so they're all the same, and I just want to show a side-by-side of how to arrange the triangles. And I like to do it separate because if I do it on the same system, the same drawing, then usually it gets all messed up and I can't see what I'm doing. So I like to separate it out, but these are all the same. Okay, so let's look for the height right here at the maximum, at the max height. So the football traveling along this trajectory gets to this point here, okay, where we found the time at the maximum height, and now we want to know how high is that. So now we're going to use this displacement vector equation a little bit different, but it's one of my favorite ways to use it, and this is why I love solving these problems with vector triangles more than your normal kinematic equations. Okay, so let's see how it works. All right, so remember that this displacement vector equation, it looks like we put our displacement vector towards the final position. And so the final position was here for the previous problem, right? X final, that's where the ball lands. And so that's where our displacement vector goes. Anywhere that we're interested in going, the final position, right? And then the velocity, initial velocity times time, right? It always follows the irregular initial velocity all the way to a height that is above the final position, and down comes the 1/2 gt squared, always, right? Gravity and this vector always points down. Okay, so this is how the triangle looked, because our final position that we're interested was actually on the x-axis. Okay, but now the final position that we're interested in is right here. So this is what we're going to do. We're going to put the displacement vector, we're going to go straight towards the final position that we're interested in. Okay, this is d vector, right? Just like we did here, we started from the initial and went straight to where the final position is, or where we're interested in. And so this is the final position that we're interested in, so we're going to start from here and go right to it. Okay, this right here is our initial velocity. So let me just label this. This is our initial velocity right here. Okay, and so in this next term here, we need initial velocity times time vector, which follows the original initial velocity and goes above the position that we're interested in. Just like here, we followed the vector all the way up until we were vertical on the position final that we were interested in. Okay, so this is v naught t vector, right? V initial t vector. And then finally, like always, right, we come down like this with our 1/2 gt squared vector, right? The last part of the vector. And remember, we're using g because it's in the y direction, and acceleration in the y direction is equal to gravity. Okay, So we have an awkward triangle up here, okay? And we can't use Pythagorean, we can't use trig identities if it's not a right triangle. And so I think you can see what this looks like if you step out a little bit and connect this h, this height, along with it. Okay, so right now we have this awkward triangle, right? And which doesn't even use the angle because this vector goes right through the angle. So you can't use it. You have to have something that's 90 degrees. So let's do something here. We're gonna combine all of this side, right? I'm gonna highlight it so it's a little more clear. So this is just to highlight everything that we're interested in. So it's the whole triangle, the big piece, where this represents the 90-degree angle. And so now we have a triangle that we can work with, okay? So how are we gonna use trig and combine this side? All right, so let's start off with sine, like we always do, because we don't have a value down here, and so it wouldn't make sense to use anything that has this as its component, like tangent has the adjacent and cosine has the adjacent. So we don't want to use those because we don't have an adjacent value. So let's look for sine. So we got sine theta is equal to opposite, and now I can use my theta now because my triangle now has become a 90 degree and encompasses the entire angle. But my opposite side, which is this entire side here, which is this plus all of this. So it's 1/2 gt squared. Sorry, we don't need to write the vector. So it's this piece here plus this piece here, right? The h, that's our opposite side. That whole thing, you could put it in parentheses, okay? Divided by the hypotenuse, which is v naught t, okay? So now let's solve for h. We're gonna pass the v naught over here, so we're gonna have v naught t sine theta, and we're gonna pass this to the other side, making it negative 1/2 gt squared equals h. And now we see that we have all the values that are necessary to solve for h. So I'm gonna rewrite h on this side, and v naught is calculated from part 4. We have 25.6. The time for the max height is 1.63. We have sine theta of 38.39 degrees, and that's minus 1/2. G is 9.8, and again the time is 1.63 squared. All of this equals to h. So if you put that in your calculator, you should get 13.06 meters. Okay, so this is the height where the football reaches its maximum height. Okay, and that represents this right here. Okay, so it's a clever way to find height, and this is one example of how we're going to be able to use this vector equation and attach other segments or other pieces, or subtract them in other examples, in order for us to have a triangle that we can use and just use trig identities and find the problem. No kinematic equations, and for the most part I feel like that's, it's intuition to think if I can combine these two, then I can use this solid side, which is perfectly fine. So we found the height. Okay, so now total time, let's block that off. So now total time of flight, right, we should be clever with this already. And like I said in the previous video, the time in the middle is the max height, but since this follows a parabolic shape, the time on this side up to the middle is the same thing as the time on the other side. So all we need to do is double up the maximum height. Okay, and that's gonna give us our total time of 3.26 seconds. So time final, all right, or total time of flight. Okay, and now for the final part, I want to move on to this drawing right here. Okay, so I want to know the horizontal distance, right? I want to know this distance right here, all the way to the end. Okay, so I know the height in the middle, I know the initial value for the velocity, I know the angle, I know the velocity in the x direction, I know the velocity in the y, so we have a lot of things, okay? And what I'm gonna do for this part is I'm gonna show you my way, or the way I like to solve for these problems, and then I'm gonna show you the kinematic way, and so you can see the difference. So it's not terrible, it's just it's preference really. So let's do this. We need to find this distance, this entire distance right here. Okay, so let's use one of our equations, right? And obviously the one that makes sense is displacement, right? Because we want to know the displacement in the x. We don't want to know velocities and stuff like that, so we're going to use this one. These two equations here are very important, and you need to memorize these two, because with these two you can solve basically most of your problems in projectile motion, kinematics, and stuff like that. So you need to commit these to memory and know when to use them. So if we want the final position, right, we're going to use the displacement vector. And so we know that this is an equation that looks like this triangle right here. And so let's draw that triangle. Where is the final position that we're interested in? Okay, and so that's going to be on the x-axis right here. So we draw our first vector straight to it. Right, we always draw straight to the area that we're interested in. Right, put an arrow, and that's going to be d vector. Okay, our second vector here is going to be v naught t. So we follow the trajectory of the original velocity, and we're going to go all the way above. This one's kind of high. That's fine. So we're going to go all the way above to right over the x final, right, the final position. And this long vector here is v initial t vector. All right, and then our last vector, which is this one here, is going to be always vertically down. Okay, and it's going to represent 1/2 g t squared. Okay, so that looks nice. We have our vector triangle on our system at a distance that we're interested in. Okay, so I'm gonna highlight this triangle here for no real good reason, but it shows you clearly that this is a 90-degree angle. Right, so that's very important. You always want to make sure that that's a 90-degree angle. And so I'm going to show you one way here to solve this, and then I'm going to show you the second way. So the first way, let's do the way I like to do it with my vector triangles and trig identities. So we're interested in this side, and so now what would be convenient to use is cosine or tangent, because in this situation we didn't want to use cosine or tangent because we don't have a value for this x. All right, we don't have the value here either, but we do have the values of this side and this side, right? Because we know the time final. All we did was double up the time at maximum height. We know gravity, we know the initial velocity from the previous video, and so we have everything over here. We just don't have this. So now it's convenient to use tangent or cosine. I'm gonna use tangent theta. Okay, tangent theta is opposite over adjacent. Okay, so we're interested in x, so let's solve for x. I'm gonna put x on this side, the tangent on the bottom, right? So that's 1/2. This is 9.8. The time final is 3.26 seconds squared. And we put the tangent down here. And so that's gonna be tangent of 38.39 degrees. Perfect. So put that in your calculator. That should come out to 65.2 meters. Nice. Okay, so this is one way to do it. Or alternatively, and again, it's just about preference. It doesn't really matter. You know, both ways are perfectly fine. It's just what you remember and what you feel comfortable with. So the second part, we can just do the displacement vector right? And so remember that this applies to x and it applies to y. In this situation, we want it to apply to x. And so what we do is we do the change in x here, right? Which represents final minus initial. So let's write that. So x final minus x initial. Okay, v initial in the x direction times time plus 1/2 ax t squared. Okay, there's no acceleration in the x direction, right? So from previous videos, we discussed y. And all we're left with is v initial x in the x direction times time. Okay, our initial position is 0, right? Because we started here at the origin, so that's 0. So what we're left with is x final is equal to v initial in the x times time. So we know from previous examples that velocity initial in the x direction is just v naught cosine theta. All right, so if you don't know where that comes from, check out the previous videos and see how to change this velocity vector here into components. Okay, so this is the same thing as writing this times time equals to x final, and we have all those values. So let's see, we have velocity initial from, velocity initial is 25.6 cosine of 38.39 degrees, and the time at the final position is 3.26 seconds. Okay, that's going to give you your x final, which is going to be 65.2 meters. Okay, you could have also put straight from here, we could have just put the answer, right? Because we were given the velocity initial in the x, right? So that's usually not the case, you know, but I just wanted to show that if you weren't given this value here, you just take it one step further and go for the initial velocity and cosine. But from here, we could have just put in what we got for the initial velocity of x, which was 20. That was given to us in the problem, and then the total time of the flight. Okay, and then we would have got the same thing. Okay, so here's one way to do it, and here's another. So it's about preference. So this concept here for this specific example, you need to understand well, because in the next couple problems, we're gonna use it to do more projectile motion problems, and we're gonna see how functional this triangle can be and how easy it could be to calculate things if we know how to combine these triangles and just use trig identities, okay? So put these two equations in your heart, and let's move on to the next examples.